So welcome everyone to this first online seminar of the new cycle that we call postdoc talks, because most of the talks between September and December will be carried out by postdoctoral researchers. And today we're very happy to welcome with us Miquel López-Suárez, who was in fact a postdoc from ICMAB recently, but now he's in Italy, although we have him here today. I would like to remember you that if you have questions, we will have some time after the seminar to answer them, and you can post them in the questions and answer icon that you can see in the bottom of your screen. And I think that's all for me. I hope you enjoyed the seminar. And now I pass the virtual floor to Ricardo Rurali, who is the host of this seminar. So welcome to you all, and thank you for being here.
Thank you, Anna. So I take over now. Welcome to all the invisible people that are connected right now. I think that Anna from her place has a full view of the current scenario. I don't, so I might be well speaking to a wall, but I hope not. So today I also join Anna thanking Miquel for accepting our invitation. Miquel did his PhD in this university and then has been fluctuating between Italy and Barcelona, a situation I'm quite familiar with because he did the first postdoc in the University of Perugia in the central part of Italy, and then he came back to work in our group, specifically with me, with the Juan de la Cierva Fellowship. And currently he is back in Italy, but now in a different place, in the beautiful isle of Sardinia, where he works in the group of Luciano Colombo. As he will illustrate in this talk today, there is a common feature in all the research fields covered, and that are all related to energy and energy harvesting. So today he will give us an overview of his work. And with this, I just shut up and give him the floor. Miquel?
Thank you, Ricardo, for the kind presentation. Well, I would like to start this seminar energy solutions at the micro and nanoscale, by showing you this image. These are two photos taken in the same place during the same event. The first one was in 2005. The second one taken in 2013, and well, I think it's quite clear the difference, the number of screens that you can see. Actually, it seems 2006, more or less, that we have more connected devices in this world than people. So actually, this is what it's called the Internet of Things. So I'm sure you heard about this concept, IoT, which means that we are planning to not only to have lots of laptops and smartphones and so on, but lots, millions and billions of devices, objects, actually, that will be connected to internet, sharing information, doing computation, everything. And actually, as I said, it's not only that we will have lots of smartphones and computers, but we are also planning to fill this world with billions and billions of small devices, sensing, doing computation, sending this information to other devices. That then this information will arrive to a node. That then this information will send to internet. From there, some final user can use this information. But at the end, if we think of this as a world filled with millions or maybe billions of these devices, then the energy that you need to power this becomes an issue. And it's not only that we have an issue with the amount of energy that we need to spend to power these devices, because even if they are very tiny devices and they need very tiny amounts of energy to work, since we are dealing with billions of them, then the total amount of energy that you need, it's quite an issue. Then we have not just this problem, but we have these beautiful high-performance computing systems that we know that we use them always more and more because we love to do computation and we need to spend a lot of energy to do this computation. And this amount of energy that we need is continuously increasing, and it's not only the problem that you need to spend energy to do computation. The problem is that when you do computation, you dissipate energy in the form of heat. And in order to evacuate this heat, you need to spend more energy. So you are doubling the budget of the thing. So this will be the framework, what we call energy problems. So we want to give some energy solutions. That's the reason of the title of this seminar. So actually what I'm going to show here, it's the work I've done maybe the last 10 years, something like this, or even more. So I've been working trying to close this gap between the energy required to operate these devices and the energy I'll be able to operate them. So all the work I will show here tries to close this gap here, and I have split this talk in 3 parts. The first one, we will talk about energy harvesting from vibration. So we will try to act on the green arrow, trying to push it upwards. And instead, in the second and third part, I will talk about computing at zero energy and using heat as information carrier. So we will try to push downwards the red arrow. Well, actually, I'm going to show a mix of, let's say, some are experimental realizations. Some of the results I will show come from molecular dynamics studies or maybe DFT studies. So I'm not going to enter into the detail of how we made these jobs, but I'm just going to comment on the general features. So let's start with energy harvesting from vibrations. So we said that we have, let's say, billions of these devices that are spread in the world, and you need to give energy to these guys to operate. Well, one solution is just to provide a battery to each one of these devices, which is maybe a possible solution, but as you know, after a certain period of time, you need to replace the batteries. And since we are dealing with billions of these devices, maybe the replace of the battery of each one of these devices, it's not a good solution. So you can think on harvesting energy from other sources, like solar energy, if you are in not a cloudy day, or maybe you can try to extract energy from mechanical vibrations, which is what we are going to comment in the next slides. So what's the easiest way, which is the easiest way to extract energy from a mechanical vibration? Well, the easiest way is to attach a mechanical extractor to the vibrating body. So doing this, part of the energy of this vibrating body is stored in the mechanical extractor. So doing this kind of strategy, you can extract energy from, for instance, from human body. You can imagine a human walking. Obviously, there is a lot of energy that you use just to move your hands, so that energy can be extracted. You can extract from this kind of system something like 4 microwatts per cubic centimeter, which is not bad. This allows you to power this kind of wireless sensor nodes that we've been talking about before. Or maybe you can extract energy from these kilohertz machines. Means I think this one corresponds to a washing machine or maybe a fridge, something like this. You can extract almost 1,000 microwatt per cubic centimeter. These are the typical values that nowadays we are harvesting from this kind of vibrations. So you know that a mechanical extractor like this is a cantilever. It can be modeled with a very simple potential energy like this one. So an harmonic potential. The device is characterized by this elastic constant that depends on the material and the dimensions and so on. You know that these kind of structures have a well-defined resonant frequency. So actually, the thing is that if you have a vibration which has the most part of its energy concentrated in a narrow range of frequencies, then the use of a cantilever, an harmonic oscillator like this one, is a good strategy since you can match the frequency of your harvesting structure to that range where you have most of the energy contained, and you can extract very efficiently from there the energy. Obviously, you can you can tune the frequency of your device by just changing the dimensions or changing the material. There are other strategies also to stiffen or to soften your structure. But the problem, obviously, is then if you don't you don't have a vibration with a well-defined frequency. So if you have a broadband vibration, what happens is that you're extracting only energy from the band where you have the resonant frequency of your structure, so you're losing the rest of the energy. So if that's the scenario, what you can do is try to figure out how to soften, how to make more flat your potential. So this can be done by adding a second term in your potential energy. This is a Duffing potential. This is how mathematically we can express this make more flat your potential. Actually, by playing with these alpha and beta parameters, you can achieve a bistable configuration like this one here. And actually, it can be demonstrated that this kind of approach allows you to, let's say, to enhance the frequency response of your system, and actually what it comes with an increase of the stored energy in the structure. It was proposed back in 2009 by this group in Perugia, led by Luca Gamaitoni. They proposed to attach, as you can see in this picture, a magnet to the tip of the cantilever, to place another magnet with opposite magnetization in front. And by playing with the distance between these two magnets, they were able to pass from a monostable configuration like this one to a stable one like this. So they demonstrated that actually, once you reach the bifurcation point, so where the stability, then you have an increase of the harvested power for this kind of systems. So we want to follow this bistable approach in order to see if we can harvest energy from vibrations, but this time at the micro or nanoscale, if we can. So I'm going to present some of the ideas that we tried to fabricate some proof of concept of this kind of devices. So that's what I'm going to show you. This is the first attempt. It was instead of relying on magnetostatic interaction, we thought, okay, we can inject some electric charge at the tip of a cantilever by applying a voltage for a certain period of time. And if you do it correctly, you can trap some charges at the cantilever. And then if you do this in two structures and you place one in front of the other, by playing with the distance again, you have this kind of bistable behavior. Well, you can see here, this is nothing, just a scheme of the experimental realization that we performed. You can see here the potential energies for different distances between charge Q1 and Q2. And here you can see the bistable, the bistable dynamics of our system. Doing this, well, we estimated, in this case, we don't have a transducing system, so we are talking only about mechanical power, not electrical power. But we were able to harvest with this kind of system something like 20 microwatts per cubic centimeter, which is compatible, competitive, or whatever with the values I showed you before. Well, this was the first example. Then we did the same again with magnets. In this case, we are dealing with the structures that are down in the micro scale. These cantilevers have a length of, I think, 200 micrometers. So actually these magnets are made with magnetic dust. So we pick up a macroscopic magnet, we hit it with a hammer, we took a small piece and we put it in the tip of the cantilever. Then we heated up the system in order to, by placing it very close to a very strong magnet in order to set correctly the magnetization. But at the end of the day, what you have is again a stable behavior, as you can see here in this the reproduction of the potential energy of the system. You can see that by changing the distance between the magnets, you can make deeper and deeper these potential wells, and you can also see how the resonant frequency of the structure goes down to the point that you reach the bifurcation point, and then when two stable states appear, the frequency goes up again. Well, I do have an estimation of the harvested power for these kind of systems, but at the end it's just another demonstrator like the one I showed you before. So once you're sure that your system is capable of storing this mechanical energy more efficiently than a resonator does, what you can think is, okay, now I want to bring this energy from the mechanical domain to the electrical domain, so to have useful energy to power our devices. So the best solution in these cases, I'm not gonna enter into the detail of why this is the best solution, but it seems that the piezoelectric strategy is the best one. So you put a piezoelectric material, for instance, on top of your mechanical vibrating structure, and then you can convert the mechanical deformation into a voltage that then you can extract to power your devices. So we thought, okay, if we want to, we want to fabricate one of these stable systems, we want also to have piezoelectric transduction, and we want to bring it down to the nanoscale. So we thought, okay, maybe the best solution is to consider just 2D material, a piezoelectric 2D material, and try to induce this bistable behavior with this kind of suspended structures. So we thought, okay, the best way to achieve bistability with a 2D ribbon is to apply a compression. This is just a schematic of the device proposed. You can see here, sorry, again. You can see here 2 electrodes and the ribbon in the middle trap. So by changing the distance between these 2 electrodes, you can apply an effective compression. So at a certain point, your system buckles. You can see here how the potential energy of your structure goes from a unstable behavior to a bistable for a compression of more or less 2%. So once you have this kind of bistability, again, you can apply a vibration to your device. You can see here the bistable dynamics of your system for a certain vibration energy. And it can be demonstrated again that this bistable approach maximizes the response of your system. Actually, with this example here, we harvested something like 5,000 microwatts per cubic centimeter. This is considering, this is an open circuit voltage. So actually, once you put a resistor in order to estimate the power generated by your system, this amount here will be drastically reduced. But however, the numbers are this here. So well, now that we know how to power these small devices, maybe we want to focus on how to reduce the energy requirements for these devices. So these devices we talk about, these are in the field. They are sensing maybe some I don't know, the humidity of a field, or maybe the vibrations in a bridge, or it could be so many things. Well, these devices will take this information. Maybe they will do some logic operations to convert this information into useful information to then send it to internet. So the approach that I want to face now is how to reduce the energy needed for doing computation. So actually, this is the trend that we've been following the last 70 years. So this is the energy required for a single switch operation for, this is for valve tubes. It was something like 0.01 joules. We are now with CMOS, the current technology, CMOS technology, we are now down to 1 to the minus 17, more or less. So we are following the right trend. We like this. If we focus on CMOS technology, we can see that we are still reducing the length of the gate of these transistors. So actually, we are going even down. We are more or less here right now. This is femtojoules, so we are around 1 to the minus 18 joules per single switching operation. And this point that you can see here, this dashed line, 3 kBT, represents the theoretical limit for electron transport-based logic device. It's quite complicated. But what I mean with that is that this theoretical limit applies only to those devices that use electrons to carry information. And this is a very important thing because of what we are going to discuss in the next slides. So we are following the right trend, but okay, this 3 kBt is a limit for an electron-based device, but what's the fundamental limit for a logic operation? Well, we now need to recall the Landauer's principle that states that erasing one bit of information comes unavoidably with a decrease in physical entropy, and thus is accompanied with a minimum dissipation of energy equal to kBt log 2. This is a very famous result of Landauer, and this corresponds to a system going from a random state to that defined state. So let's see what does it mean. Well, erasing a bit of information means that we have a bit encoded in we have a bit of information encoded in a system, so you need a system with 2 stable states. Again, we have this bistability. And reducing the information, so this decrease in physical entropy comes from the fact that the erase of a bit of information means that you start with the system in an unknown logic state. So you start 50% of the times with the system in the 1 logic state and 50% of the times with the 0 logic state. Then you apply a protocol of forces to your system, and you end up with a system with a 1 well-defined state, let's say the 0 logic state. So if you calculate the entropy for the initial state and the final state, you apply the second law of thermodynamics, you will find out that the decrease of entropy is kB log 2, and therefore the energy that you need to produce this decrease of entropy is kBt log 2. So this would be the minimum amount of energy for an erase of a bit of information. So what happens if you apply this principle to a switch operation? I want to recall now that we were talking about switching energy. So nowadays, for a switching event in a electron-based transport device, you need to spend 3 kBt. Let's see what happens for the fundamental limit, so despite of the kind of technology that you use to do the operation. Well, a switching event means that you start with a well-defined logic state. So let's say we start with the 0 logic state. You end up with another logic state, in this case the 1 logic state. So you have the same entropy at the beginning and at the end of the process. So you have no change in entropy, so you have no dissipation. So in principle, switching operation can be performed at 0 energy. Okay, it was Landauer that said in the very same paper, he generalized this result associated with the reset operation to the cases where there was a decrease of information between the inputs and the outputs of the computing system. Okay, so let's see what Landauer means with this decrease of information of your computing system. You know that computers nowadays are, let's say, are based on assembling logic gates in order to perform logic operations. So you can, for instance, have an AND gate, an OR gate, NOR gate, and so on. There are so many of them. You can see here the truth table for these gates. So you can see you have 2 inputs that can be 0, 1, and you have just one output. And this is what Landauer means when he said a decrease of information. Because you have 2 inputs and just one output. So if I tell you, for instance, if we consider the AND gate, okay, you have a 0 logic state in the output. Can you tell me which were the inputs? No, the answer is no, you cannot. So this is logically a reversible operation. So Landauer said, okay, if you have this kind of operations, if you have a system that performs this kind of operations, anytime that you operate it cyclically, you need to spend a minimum amount of energy. That in this case, just by chance, is the very same amount. He said is kBt log 2, because you have 2 inputs and just one output. Okay, let me at this point present you these 2 subcategories of devices. You have what it's called a combinational device or sequential device, depending on if the device itself can remember the last state. So for instance, let's say that a combinational device, in the absence of any external force under equilibrium conditions always, and they are in the state S0. When an external force is applied, they switch to the state S1. And once you remove the force, they recover the original state. Instead, for a sequential device, you have that once you apply the force to switch the device from S0 to S1, and you remove the forces, the device stays in the state S1. The device doesn't recover the original state. So this is called a sequential device. And actually, what I want to stress here is that actually computers nowadays are made with transistors, which are these kind of devices that I have depicted here. And actually, a transistor is something that can be, you can think on a transistor like a tap. So it's a kind of device that, in absence of forces, gives you zero current, zero flux of electrons. Once you apply the force, in this case, once you apply a voltage in the gate and a voltage between the drain and the source, you have that the drain current increases. So at this point, you can say that you have the logic output equal to 1 in the output of your device. But the thing here is that once you remove the voltages in your device, you recover the original state, which is current equal to 0. So actually, a transistor cannot be modeled through this kind of bistable potential, but it's much better defined with this kind of approach. So from my point of view, a transistor can be modeled with a monostable potential energy. So in the absence of forces, you have your system, which is at equilibrium with an output equal to 0. But once you apply a force, you can disrupt your system and it gives you the output equal to 1. But once you remove the forces, it recovers the original shape. So this is just to stress that I don't want to model a transistor with a bistable potential, but with a monostable one. And actually, as we said before, the minimum amount of energy that you need to spend when you operate a transistor, since a transistor is an electron transport based device, it's 3 kBT. So you cannot reach this theoretical Landauer limit. So we thought, okay, we are not going to use transistors for doing our operation. We are going to use mechanical structures. So we are planning to implement a NOR gate that with transistors can be implemented with this scheme here. But as I said, you can remove transistors and put other kinds of switches which are not based on electrons transport. And then you can operate again this gate to perform properly the operation. So actually, this is the logic gate that we proposed. This is a cantilever with 2 probes. You can see here. So this represents output, the first output, the first input. This one here is the second input, and the output of the operation is encoded in the bending state of the cantilever. So if the cantilever is not bended, then the output is 0. If the cantilever is bended, then the output is 1. So this is a scheme of our device. You can see here that once you rise up the voltage in one of the 2 probes, the cantilever bends, so the output can be read at this point here. You have the output equal to 1, and then you remove the forces and you recover the original state of the cantilever. So to a certain point, this is comparable with the functioning of a transistor. So we want to apply, we want to perform this OR operation with this cantilever. You can see here the probability density function of this cantilever for the different inputs of the logic gate. So this is the probability density function for the input equal to 0, 0. So the system, the cantilever is not bended. When you apply a voltage to one of the 2 one of the two probes, you have a band that makes the cantilever oscillate around 0.9 more or less nanometers. And when you apply a voltage to both of the tips, you have a displacement which is slightly higher than before, but again, it's very close to the 0,1 or 1,0 input states. So well, we can do this cyclically. We can do it spending different periods of time for doing the operation. And if you know the internal energy of the system and you can record the trajectories of your system while doing this operation, you can compute the Stratonovich integral, which is this guy here, which allows you to compute the work performed on the system while you are operating it. So while you're applying these voltages to the tips. So if you know the work on the system and you know the internal energy, you can know the dissipated heat. So this is what we did with our system. We operated it cyclically with different operation times, and you can see that if you do this operation slowly enough, we are talking about milliseconds. So for sure, this is not competitive with a transistor. But what you can see is that at a certain point, what you're dissipating is well below the Landauer limit. So we say at this point that we are capable of implementing a logically irreversible operation with a physically irreversible system. So we are demonstrating that there is no link between information, so with informational entropy and with physical entropy. There is no such a link, as Landauer said in his article. And actually, we are saying that you can perform all kinds of logic operations spending almost zero energy, almost. You can spend a value of energy as low as you want, as long as you operate your system slow enough. Again, I'm not saying this is a new disruptive technology. We are not going to use transistors anymore. We are going to build mechanical computers because this is the future of computation. No, I'm just saying that with this kind of systems, you can provide evidence that logically irreversible operations can be performed at zero energy. So at the end, we are putting our point here. So below the 3 kBT theoretical limit for electron-based devices, and well below the Landauer limit, as I presented before. So, okay, now we know how to power these small devices. Now we know how to reduce the energy required to operate them, to do computation. Now let's see what can we do with the energy that we are still producing in form of heat, that nowadays needs to be evacuated, as I said before. But some people some time ago thought, okay, maybe this heat, this wasted energy, can be not only evacuated but can be used for doing useful work, so to do computation. So actually, the idea is, instead of using electrons to transfer to carry information, we can use phonons. So instead of using this kind of electron-based transistors, we would like to have transistors based on the flow of phonons. So we will change the information carrier from electrons to phonons. We would like to change the inputs from voltages to temperatures to have a fully thermal device, and we would like to change the output from electrical currents to gate fluxes. Well, that would be the optimal thing to do, but I'm not that brave, so I just focused on thermal rectification, which actually is, let's say, it's a key thing in order to be able to obtain a fully thermal transistor, but obviously just a small part of it. So to start, what's thermal rectification? Well, you have thermal rectification whenever you have a system that is capable of having a high phonon flux in one direction when you apply a certain thermal bias to your device, but it presents a very low thermal bias when you put it in the opposite thermal bias. So, for instance, in this case, we have a material, we put it within this thermal bias, a negative thermal bias, so we have a very high heat current flowing through the device. Instead, when we put the opposite thermal bias, we have a small heat flux. So under these conditions, you can define this rectification factor, and that's all. You have rectification. Actually, the thing is not to have rectification, but to have high values of rectification. Okay, so how can you achieve this thermal rectification concept? Well, you can, for instance, a very easy way to do that is to put in contact two different materials, A and B, like this. You know that these materials can be modeled, can be defined with through their thermal conductivity. For instance, we have depicted here the thermal conductivity for material B with this orange line, and the thermal conductivity for material A with this green line. So when you apply a thermal bias to this device, a temperature profile will be created, and actually it can be demonstrated, roughly speaking, that the heat current flowing through the device under these conditions it's proportional to the area contained below these two areas. If you look at this graph, you will see that from bias, we are integrating the thermal conductivity for material B from Tc to Ti, so corresponding to this thermal range here. We are integrating the thermal conductivity of material A from Ti to Th, and the sum of these two areas here will give us the heat flowing through the device. If you do the same, considering the opposite thermal bias, you can apply the same idea to this graph. To this graph here, and what is apparent is that by constitution, these two areas, so the areas computed for the upper graph and this graph here, are different, and therefore the currents are different, and therefore you have a certain amount of rectification. Actually, once you know the thermal conductivities of material A and B, there is a very simple model developed by Dames, which tells you that the maximum amount of rectification that you can achieve with these two materials depends only on these exponents of the power rows that you use to fit the thermal conductivities. And just by considering these two indexes, these two exponents, and the thermal bias that you're applying to your system, you can obtain the maximum rectification. A problem with this approach is that at high temperatures, most of the materials show very similar exponents. So, sorry, I see now that I have N1 here and N1. This should be N2. However, the problem is that at high temperatures, most of the materials have the same or very similar exponents, so at the end you end up with a rectification factor which is very, very low. But let's see what happens if you apply this to a micro or nano system. For instance, we consider it, we start with this system, which is a system made of graphene and bilayer graphene. In this case, we performed a molecular dynamics study. You can see here a scheme of our device. You can see that when you apply a thermal bias between two ends of this device, you create this thermal profile along your device. So we were able to compute the thermal conductivities for these two materials, for graphene and bilayer graphene. We obtained, as you can see here, different exponents even at high temperatures for the two materials. You can see here 0.97 for single layer graphene and 0.4 for bilayer film. So in principle, we can have rectification with the system. The base model gives us an estimation of -2% under a thermal bias of 200 kelvins and something like -5% of rectification for a thermal bias of 500 kelvins. But surprise, surprise, we did also let's say we performed the real simulation. So not only computing the thermal conductivity to infer which is the maximum rectification that we could achieve, but we also actually applied the thermal bias. We computed the heat flux under a certain thermal bias and under the opposite thermal bias, and we obtained these thermal rectification factors for the system for different. You can see here the parameter phi, which is nothing but the ratio between the length of the single layer part and bilayer part. And you can see that we are obtaining rectifications that are clearly not only in disagreement from quantitative point of view, because we are obtaining 5% and 15% of rectification, but we have also a disagreement from the qualitative point of view, since the Davis model predicts rectification of -2 and -5%, and we're obtaining rectifications that are positive. So, or we are doing something wrong, or there's something wrong with the Davis model, or obviously there is a disagreement here that it's not acceptable. So what we did is to look into detail in this interface between the two materials. You can see here that actually there is some problem with the temperature definition at the interface between monolayer and bilayer graphene. But to comment on that, let me consider again two generic materials, A and B. The fact is that when you put these two materials in contact, there is what is called a thermal boundary resistance created at the interface. So if you zoom in into the thermal profile, you will see that you have this kind of step, which is indicative of this thermal boundary resistance. And actually, the particularity of this thermal boundary resistance is that a difference with what happens with material A and B, the resistance of this interface do not depend on the length of the interface. Well, it's not that it does not depend on the length of the interface. It's that the interface of the system, it's fixed. It depends on the materials that you put in contact. It's not something that you can choose. It's different from the resistance of material A and material B, which depends on not only on the temperature, but also on the length of the piece of material A or material B, and also on the cross-section of the material. So again, for the interface, we don't have this dependency with the length. But you do have the dependency with the temperature. So actually what happens is that when you apply a thermal bias, this interface will be found at a certain temperature. And then what, for instance, you can see here for a material A and B equal to silicon and gallium phosphide, you have the temperature of the interface for a forward thermal bias varies like this. This is again against the factor phi, which represents the ratio between the length of segment A and B. You can see the temperature of the interface for these different values of phi, and you can see that under the reverse thermal bias, you have different temperatures at the interface. So this means that what you will have is different values for the resistance at the interface. And this has a huge effect on the total amount of rectification that you get. Actually, if you look at this graph here, where I show the rectification obtained for different values of phi, you will see that the maximum value is something close to 2%, with what actually is in good agreement with the prediction of Davis model for these two materials. But this is just considering the bulk contribution to rectification, because if you take into account also the weight, the role of the interface, what you end up is with a rectification like this. So if you pay attention, you will see that you don't have the same rectification values. Here, for instance, I have 5%, while for the PAL counterpart is just 1%. So here I am enhancing the rectification due to the role played by this interface, but not only. For certain values of feed, I can achieve also rectification values that are negative. So something that remembers us what I obtained with graphene, as I pointed before, a rectification that was positive when the Thames model applied only to bulk materials predicted as -5%. So actually, what we've shown before, this change on the sign of the rectification factor is a sign of the role of the interface. We performed also a set of simulations showing what was the rectification factor as a function of the total length of our device. And as you can see, when you increase the length of your device, so when you are recovering the bulk behavior of your system, so in some sense you're reducing the weight, the role that the interface is playing, what you do is to recover what the Thames prediction of that bulk value for the rectification factor. So, well, I think I'm done. So I've been able, I have shown you how to power these small devices with environmental sources, in this case with mechanical vibrations. So after show you how to power these devices, I showed you, I gave you some ideas on how to operate logic devices at zero energy. And finally, I have shown you some of the work I've done regarding the role of the interfaces in nanoscale systems. So, well, that's all from my part. Thanks for your attention. And there are questions or?
No, Miquel, thank you. Thank you for your talk. I don't see any questions for the moment. I don't know, is Ricardo here? Maybe he wants to ask some questions or some comments about your work.
Yeah, well, let me get here and
no, I cannot accept questions from Ricardo. He's
no. He will, because of course I'm going to ask about the central part of this talk, which is the one that he carried out between his stay at ICMAB. Thank you for a specific question, but of course this is a very catchy research topic. And so I just wanted to know from Miquel, if he knows, what is the state of research in that line of work. If it's something that it has a flare of enthusiasm at some point and then the interest decayed, or people are still working on that, and what are the challenges right now?
Well, from my part, I had to quit this topic just because I changed my place of work, so I changed the topic. I do know that it's a very hot topic still now. People is working right now in mainly in other implementations of this kind of non-dissipative logic gates using different technologies. I'm sure that there is a group in Peru at least working with magnetic systems, so something that it's more related with technologically feasible implementations. And I know also that there is a group working with non-adiabatic transformation. So I'm not an expert on that, but I think they are trying to fabricate devices that are capable of, they can be operated adiabatically, but with very fast operation times. So they are applying a kind of force protocols that are able to, they are able to freeze the different states of the logic state. So they can switch very fast. And once you switch very fast, in principle, you should dissipate this excess of kinetic energy that you have in your system, that they are able to freeze the system very fast and to dissipate almost zero energy. So more or less, these are at least it's what I remember now.
Okay.
I have a question. In fact, I mean, it's only from the first part of the seminar that I could understand more or less. It's about the energy consumption now worldwide using data, like storing data and using data. Do you know if it is really a very big amount of energy that we are consuming now for all the, you know, Google, all the cloud information? How is the amount, or how can we imagine how much energy is consumed?
I cannot tell you the numbers. I know I just learned this introduction. It's something that we repeat.
Wait, I cannot hear. Okay, now.
So, but this energy, maybe I was not very clear in the introduction. This energy harvesting strategy is mainly thought for autonomous wireless sensor devices. So this energy harvesting strategy is very useful when you have, as I said, lots of these devices spread in a field. They are wireless, so you cannot reach them. You need to power them. So it's not a problem of the amount with the amount of energy that they require to be operated, by the fact that you cannot reach them, you cannot power them, you cannot put a battery on them, you cannot attach a wire and send the energy there. So you need to extract energy from environment, because it's the only solution. So again, it's not a problem of the total amount of energy that you need, but the fact that you have all these guys spread in the field. But no, I cannot.
Okay. No, don't worry. I was just wondering that nowadays, I guess that there's a lot of energy consumed that we are not aware of, no? The energy that you use sending an email or storing documents in the cloud or using your smartphone, so on.
Sure.
But yeah, that's a different topic, I guess. Sorry.
No, well, you see here in the introductive part, I put this graph. It was in 2006. It's quite old, this graph, but well, this is a funny thing. You are, for storage network and servers, you are spending something like 3 gigawatts in each one of these power centers, and then for cooling, you are more or less spending the same. So something like this, gigawatts. We're talking about gigawatts.
Yeah. Okay. There is no questions in the seminar, but I don't know, Ricardo, anything else or any comment?
No, I was just thinking that now the battery of my smartphone died during the talk, so I really feel this problematic we're discussing now. So now I have to go plug it in because somebody will call me. I will need it. No, that's all on our side. So I guess maybe you can now do the official closure, and we can thank Miquel again.
Yeah, it was very nice, Miquel. Thank you for accepting to join us for this seminar. And I hope that you go on with this interesting research of yours. And thank you, Ricardo, for proposing the speaker in this case. And thank you all of you for being here. Probably the talk will be in YouTube, so we will be able to see it. I have to talk to Miquel.
I think it's no, it's okay.
We'll see. Next seminar is in 2 weeks, and we'll talk about a totally different topic. We'll talk about nanoprobes for drug delivery and bioimaging. So a totally different topic by Judith Mulbrand. So thank you, and see you later.
Thank you, Anna. Bye.
Bye. Thank you.